Well, as we say in English, how time flies when you're having fun. So we're now at the final meeting of this course, and while preparing the slides, it became very clear to me that there were many subjects I would like to discuss that I really will not have time to discuss. At the end of this set of slides, I've added a short bibliography to help people read things on the subject that are related to my lectures. So that should help. There will be things that I'll only touch on in the lectures that I would like to discuss in greater detail, but I'll have to settle for just pointing you in the right direction. So today I would like to begin by talking about things related to the Seiberg-Witten equations and their role in the theory of Einstein metrics. And let me remind you of a definition I introduced last time. So if you have a smooth, compact-oriented four-manifold with B plus at least 2, then a cohomology class, here I'm emphasizing that it's in a certain vector space, the second cohomology with R coefficients, but in fact this will be an integer class. It's called a monopole class if there's a spin C structure on M whose first Chern class with real coefficients is A, or equivalently, if C1 of L mod torsion for this spin C structure is this element of real cohomology. So remember that the integer cohomology does not, in general, inject. There's a natural map from integer cohomology to real cohomology, and that map kills the torsion. Otherwise, it will prevent the free part of the integer cohomology and the real cohomology as a lattice. All right. So the criterion to be a monopole class is that you have a spin C structure such that for every metric on the manifold, there's a solution of the unperturbed Seiberg-Witten equations. And so if that's true if you can find a spin C structure with that property, for every metric, there is a solution of these unperturbed Seiberg-Witten equations, then we say that the first Chern class in real cohomology of that spin C structure is a monopole class. So there's a very important proposition, which is that if you have a smooth, compact-oriented four-manifold with B plus greater than or equal to 2, then the collection of all monopole classes, first of all, it's a finite subset of the cohomology. The second thing is that this finite subset is invariant under reflection to the origin. So if you multiply a monopole class by -1, you get another monopole class. And finally, that set, it's almost obvious from the definition, that is something which has to be a diffeomorphism invariant of M. So this is a statement about, you have a smooth manifold, you consider all smooth metrics with respect to that smooth structure, and ask that there's a solution of the Seiberg-Witten equations for a particular spin C structure. The proof of finiteness in this generality involves the fact that if you have a solution for a particular metric, so choose some metric, and look at this spin C structure for which we know that we're told, I mean, this is a black box, right? We're not really told right now why there's a solution. You need some other machinery to show that a particular spin C structure has this property. But just it's a sort of useful conceptual tool to say, look at those spin-C structures with this property that for every metric you can solve this, there's a solution of the Seiberg-Witten equations. Okay, so now choose some particular metric on the manifold. We have a fixed spin-C structure we're talking about, and then one of the basic inequalities, curvature inequalities that we proved was that if you take the integral of the scalar curvature squared of this metric, then that's greater than or equal to a certain multiple of C1 of L self-dual piece squared. So there's a lower bound for the integral of the scalar curvature squared in terms of this. So you take C1 of L, take its harmonic representative, take the self-dual piece of that, now take its cut product, you take its square in the sense of cut product, and then multiply by a certain constant, 32 pi squared. So if you have any unit element of the self-dual, so this would actually be something represented by a self-dual harmonic 2 form with respect to G. But let's just say it is a unit vector in this space on which the intersection form is positive definite. So for a unit vector in this subspace of the second cohomology, then you automatically have an upper bound for C1 of L, where L is the determinant line bundle associated with this spin-C structure. C1 of L, dot that unit vector, take the absolute value of that number, and then that has to be less than 1 over the square root of 32 pi squared times the L2 norm of the scalar curvature of G. Now, this factor, the main thing is that this factor is less than 1. So let's just keep it simple and say that's less than the L2 norm of the scalar curvature. I just want some upper bound. This is a kind of soft application of geometric ideas. We're not really trying to get out refined information about Riemannian geometry in this argument. All right, so V dot C1 absolute value is less than the L2 norm of the scalar curvature for that metric. So there's some constant depending upon the metric happens to be the absolute. It happens to be the L2 norm of its scalar curvature is an upper bound for the absolute value of V dot C1 of L. All right, so if you like, so this would be true whenever we just use the fact that this is a solution of the Seiberg-Witten equations. The definition of monopole class says that for every metric you have a solution. So if A is of the form C1L, then here we can think of this as just the cut product of V and A, because that will only see the self-dual part, since V is self-dual with respect to G. Okay, so V cut product A, or V intersection form A, has absolute value that's bounded by a constant depending on G. And that's true for every monopole class. So notice this constant only depends on the metric, it doesn't depend on which class you have. All right, so now the trick is to use an observation of Donaldson's concerning the period map. For any particular metric, the second cohomology decomposes. So the second cohomology can be represented by the harmonic 2 forms, and those are the direct sum of the self-dual harmonic 2 forms and the anti-self-dual harmonic 2 forms. But that, and so here, just for emphasis, I mean, there's a nice null cone in the second cohomology consisting of things that have intersection product with themselves equal to 0. That's the cone. H plus is on one side of it, H minus is on the other side. That's a statement that doesn't depend upon the metric, but actually as you change metric, this decomposition changes. They remain orthogonal to each other with respect to the intersection form, but here, remember, this is an indefinite inner product, so if you haven't really thought about indefinite inner products, orthogonality looks a little bit different than it does in the positive definite case, right? But in particular, these are intersection form perpendicular to each other, and so you might as well just keep track of one, the self-dual subspace. So the dimension of this subspace is B plus of the manifold that's independent of the metric, but the particular subspace you get depends on the metric. So Donaldson's observation is if you look at the map from the smooth metrics on M to the Grassmannian of B plus dimensional planes in H2 on which the intersection form is positive definite. All right, so this is a Grassmannian of dimension B plus times B minus. But it is, it's the non-compact dual of the usual compact Grassmannian. So there's a natural map from metrics on M to this Grassmannian, sending G to the subspace spanned by the self-dual harmonic forms. And Donaldson's observation is that this is a submersion. As you vary the metric, so there's a map from the tangent space of metrics to the tangent space of the Grassmannian, and that's always surjective at any point. So a little corollary of this is that if you look among all metrics on your manifolds, look at, for each metric, take the self-dual subspace minus 0, and now take the union over all metrics. That's an open set in H2 of MR minus 0. Right? So as you vary the metric, in particular, you can get, if you've got a particular positive definite plane, when you look at nearby metrics, you can get any nearby positive definite plane, and in particular, the things that are in those will be open. But this is a silly but important fact, right? You take any open set in a vector space, it spans the space. But that means that you can find a basis for H2 consisting of vectors which are self-dual with respect to some metric. So in particular, you can find a collection of pairs that consist of a metric and a cohomology class where these cohomology classes actually form a basis for the second cohomology. And of course, we can go on to normalize. We cannot make this a pseudo-orthonormal basis. Right? These are all in the positive directions. You could sort of imagine your basis as being a very, very tight little collection of vectors, but they still span the space. All right, so before we made a statement, if you had a particular metric and a particular vector which was self-dual with respect to it, there was the inner products of that vector and a monopole class. There's an a priori bound on the size of that inner product, but now you have the same principle applying. Now we have B2 different metrics and B2 different cohomology classes where we have similar bounds. So these vectors are kind of very close to each other, but nonetheless, when you look at this set of equations, that's exactly that's giving you the definition of a certain parallel pipette. It happens to be a kind of strange, broad one, but the point is it's still compact. All right, so that means that our set of monopole classes is contained in a compact parallel pipette. But it's also, these are integer classes. So this is a discrete subset of a compact set of a compact subset. It must be finite. Okay, so that's the proof of finiteness. It's a soft proof depending upon one non-trivial calculation, and that is the basic curvature estimate that tells you that you can, that the L2 norm of the scalar curvature gives you an upper bound for any monopole class self-dual piece squared. What about the reflection invariance? This is, again, a kind of a soft argument. There's a natural complex conjugation. If you take a spin C structure, it has an associated twisted spin bundle, and you can take the conjugate bundle. But that conjugate bundle actually is also the twisted spin bundle for a different spin C structure. Okay, so in fact, when you do this, there's a natural map from solutions of the Seiberg-Witten equation with respect to one spin C structure, and then you can just take the conjugate of the take the complex conjugate of the twisted spinner, and here A will correspond to a certain connection on the determinant line bundle. This determinant line bundle will be the dual, but it has a dual connection. Okay, so the line bundle is actually the determinant line bundle of this rank 2 complex vector bundle, and this operation has actually the way it acts on first Chern classes of spin C structures is just multiplying the first Chern class by -1. So whenever the A is a monopole class, so it's represented as the first Chern class in real cohomology of the determinant line bundle, or of if you like, a B plus, then minus A, so multiplied by -1, you get another monopole class. All right, so there are a couple of beautiful, simple invariants that you can define with a manifold using this observation. So the first one I'd like to, this is one that just really depends upon depends on the finiteness of the set of monopole classes. So if you have a smooth compact oriented four-manifold, and you assume your B plus is always greater than or equal to 2 here, what we can then do is, we've used C to denote the set of all monopole classes, and then if C is not contained in 0, so if it's contained in 0, that means that the only monopole class, it could be that C is empty, right? Maybe there are no monopole classes. Another possibility is that maybe 0 is a monopole class, but there are no others. So if there's more than one monopole class, then we define the bandwidth of M to be, what you do is take differences of 2 monopole classes and think of those as being in the free part of the cohomology, and ask what's the largest integer that divides that difference. One could just say the largest integer here. It turns out, these are always congruent mod 2 because they all have the same reduction mod 2 as W2. So historical artifact, when Masashi Shiat and I introduced this notion, we put a factor of 2 there just to cut it down. But conceptually, you're saying the bandwidth is, you look at pairs of monopole classes and ask, in a kind of algebraic sense, how far apart they could be in terms of divisibility in the integer cohomology. This is a great word, bandwidth. We introduced this in it's probably about 2003 through 2004. Many people have jumped on this because everybody, there's a lot of bandwidth problems on Wi-Fi and so forth. So this word is floating around a lot more, and unfortunately, it's been used for many other things mathematically. I believe we may have made the first mathematical use of it. So I won't change the term. It's bandwidth. All right, so it's the largest. It's a question of divisibility. What's the largest divisibility you can get by looking at differences of pairs of monopole classes, thought of as elements of the free part of the integer cohomology? All right, and so of course here we assumed that the set of monopole classes is not empty and it's not just zero. In either of those other cases, we just define the bandwidth to be zero. All right, so this assigns to a smooth compact manifold a specific natural number for each but it is something assigned to the particular differentiable structure. And what I'm going to be discussing is how does this bandwidth depend on the choice of smooth structure. So here is a wonderful, simple example. So we've talked about those spin-C structures that arise from almost complex structures on M. If you have an almost complex structure on M, it has a first Chaire class, right? And so, and you could ask whether the spin-C structure actually is whether that first Chaire class is a monopole class. That would happen if this spin-C structure had the property that for every metric there's a solution of the Seiberg-Witten equations. So the simple invariant that I described last time, which was really introduced by Witten, and actually the Z mod 2 version, I think it was actually originally Kronheimer and Mrówka. There is a Z2 valued invariant. You just count the number of points in the moduli space for the perturbed Seiberg-Witten equations for generic perturbation. And so for generic perturbation, you'll find that the count mod 2 is independent of choices. If that is not 0 mod 2, then it follows that there is a solution of Seiberg-Witten, the Seiberg-Witten equations for every metric. So there's a different terminology. Sometimes these are called basic classes. So the amazing point is that if B1 is even, and J is integrable, that happens if and only if you can find a Kähler metric that's compatible with all of the information. Then its first Chaire class is a monopole class. Here is something that is very remarkable in 4 dimensions, and it's unknown whether this can happen in other dimensions or not. Typically, if you have a four-manifold that has a spin-C structure, then, if you have a four-manifold that has an almost complex structure, then there are typically lots and lots of other almost complex structures. You can change the first Chaire class. So there are very mild requirements on the first Chaire class as an integer, as an element of cohomology. If you want it to be the first Chaire class of an almost complex structure, the only things you need are that its square is 2 chi plus 3 tau, and that its reduction mod 2 is the second Stiefel-Whitney class. So actually, if you assume that the intersection form is indefinite, and let's say B plus is greater than or equal to 2, like we're doing, it'll turn out that if there's one C1 that arises from an almost complex structure, there are infinitely many choices of C1 that arise for almost complex structures. But the amazing thing is when you're saying, well, here's an almost complex structure, could I deform that to be integrable? Well, a requirement from this theory is that if there is an integrable complex structure that represents that first Chaire class, then in fact its first Chaire class is a monopole class, and we know there are only finitely many monopole classes. Right? So that means that most almost complex structures on a four-manifold, with very mild extra hypotheses, most almost complex structures cannot be deformed to be into integrable complex structures. It's completely open in higher dimensions. Is there any obstruction if you give me an almost complex structure on a 6-manifold? Can it be deformed into an integrable structure? And of course, this We just don't have any idea. So there's an almost complex structure on S6. Can it be deformed to be integrable? We have no idea. So I don't, by the way, recommend thinking about that problem too much because it's a huge waste of time with current technology. If you don't have some new piece of technology, you're not going to make any progress on that question. Maybe the time will be ripe in the next 20 years, maybe it'll be a century before someone understands how to solve that particular problem. Anyway, dimension 4, there are very strong constraints beyond, if you have an almost complex structure, most of the time it cannot be deformed into an integral complex structure. When it can be, when C1 of an almost complex structure, if the almost complex structure is represented, can be deformed to an integral one, then in fact its first Chaire class must be a monopole class. And in particular, it's actually a more special monopole class. It is one where, for example, the classical Seiberg-Whitney invariant even with Z2 coefficients would be non-zero. All right, so for example, if we take the manifold K3, which we discussed at some length, on K3 one can show that the only monopole class is the zero cohomology class. All right, so zero is K3. Remember, it is a simply connected compact complex surface where C1 is 0. So 0 is a monopole class on K3, but on the other hand, it takes a little more discussion to show that that's the only class. Okay. On the other hand, Kodaira discovered, I guess in the early 60s, that there were a lot of other compact complex surfaces which he could show were homotopy equivalent to K3, and he was fascinated by the question, are these diffeomorphic to K3 or not? So the fact that they're homotopy equivalent to K3 is easier to check than things like, are they homeomorphic? Are they diffeomorphic? With the results of Friedman, the fact that they're homotopy equivalent to K3 will imply that they're actually homeomorphic to K3. But what about diffeomorphic? So the way the Kummer model of K3 was to take a 4 torus modulo Z2 action. I have a specific reason for thinking about the Z2 action the following way. Think of T4 as a product of two tori, and each 2 torus has a so-called Weierstrass involution. You flip the 2 torus over, that has 4 fixed points. Right? So you think of it as sitting on the table, you flip it over, you've rotated it through 180 degrees around a certain axis, and there are 4 fixed points. So when you do that simultaneously on T2, on the 2-factor T2s, then there are 4 times 4, 16 fixed points. Now, when you, this quotient, though, it has a natural map to T2 mod Z mod 2, right? So the Z2 action acts simultaneously on both of these elliptic curves, as algebraic geometers like to call T2 with a particular complex structure, an elliptic curve, for reasons which are historically kind of unfortunate. That's to say that you can get any Riemann surface of genus 1 actually as a double branch cover of CP1 with 4 branch points. And so here we've got a natural holomorphic map, but initially, right now we have this complex orbifold, but we can make it into a manifold by first blowing up those fixed points before we add mod out by Z2. When we now take the 1 2 torus and mod out by Z2, we get a certain orbifold model that looks like CP1 with 4 orbifold points. Forget their orbifold. We have a holomorphic map from K3 down to CP1, and it happens that there are there are four points that are not regular values of that map. All right, so you can now take some generic point, some regular value of this projection, and so its inverse image would just be a copy of the 2 torus. Okay, so it might take a little bit of thought here. You mod it out by Z2 and the other factor, but that's just saying that 2 things that were generic fibers of the map to T2, either one of them would be a model for the inverse image of this regular point in K3. Now, the trick is to pull out, so here we have a certain 2 torus, and we can, there is a trick for replacing that. So we're going to take out that 2 torus and put in a new 2 torus, but that's thought of as the old 2 torus modulo an action of Z2L plus 1, of a cyclic group of order L plus, 2L plus 1. So the reason that you can do this is that, so the local model would be that you have T2 times a disk in the here, and now we're going to mod out by this cyclic group how it's going to act by a rotation of order 2L plus 1 on the disk, and choose a point. It's here T2, it's if you like R2 modulo a lattice, choose a point in there of order 2L plus 1. Now, so that so now adding and rotating in these 2 factors would be the model for how you're going to act. But when you mod out here, so the quotient of this disk by this rotation group is itself a 2 disk. You can identify that with a 2 disk, and then the exercise is that away from the origin, in fact, this is a trivial T2 bundle over that 2 disk. So what you can now do is, so in the original model we had a tubular neighborhood of T2 that looked like T2 disk. Pull that out, and then we plug in this guy instead, where the gluing, of course, is away from the 2 torus that we took out. So that introduces a new holomorphic curve. There's a natural complex structure on this modified K3 where we put in a different 2 torus that, with respect to the original 2 torus, should be thought of as a fiber 2 torus modulo a group of order 2L plus 1. So what we get in this way, you can check that it's still spin, it still has the same B plus and B minus, it's homotopy equivalent, still simply connected. It's homotopy equivalent to the original K3, but on the other hand, its first Chern class is not trivial. In fact, its first Chern class is minus 2L times F, where this fiber F is the new homology class that we've introduced by sticking in this short torus. So we've taken the original K3 had first Chern class 0 in homology. This is not, F is not the 0 class, so this C1 is not 0, and in fact it's divisible by 2L. So, but on the other hand, this is the first Chern class of a complex structure on this new complex surface, and so its first Chern class is a basic class and therefore a monopole class. It's divisible by 2L, and when you look at the difference between that and its minus that C1, then that will be divisible by 4L by the definition of the bandwidth that says the bandwidth must be at least 2L. All right, so the bandwidth of this, we've just created a different complex surface which is homotopy equivalent, and in fact by by Friedman's theorem, this is actually homeomorphic to K3, but its bandwidth, the bandwidth of standard K3 would be 0. Here, I'm not trying to calculate the bandwidth exactly. We know that it's certainly greater than or equal to 2L. And on the other hand, the bandwidth is some finite number, right? So I've defined this in a soft way. I'm not trying to actually calculate it. If you work hard, you can prove that this is, in fact, just the bandwidth turns out to be 2L. We don't need that. The point is that we have a lower bound that goes to infinity as L goes to infinity. So we have a sequence of different smooth structures. Each of these four manifolds is arising as a complex surface. It's done by this kind of, it's what's called a log transformation, invented by Kodaira. And in terms of the smooth structure, the bandwidth of that complex, of that smooth structure goes to infinity as this number L, this integer L, goes to infinity. But that means that among these, smooth structures we found on the topological K3, that we must be seeing infinitely many diffeomorphism types, because if there were only finitely many diffeomorphism types, there would be a maximal bandwidth. We've just said that the bandwidth goes to infinity among this sequence. So the topological four-manifold, by the way, like I said, if you work harder, you can prove that those are exactly the bandwidths, and that each of those each of those smooth structures we've described on K3, those are all distinct. But here, I'm interested in a softer point, namely that K3 has to have infinitely many smooth structures. Among that list, there must be infinitely many of them that are distinct. So K3 has infinitely many smooth structures, but exactly one of those, the original K3, is the only one that could admit an Einstein metric. Right? So remember, K3 is in the case where 2 chi plus 3 tau, twice the Euler characteristic plus 3 times the signature, is 0. So this is in the boundary case and this number is actually only dependent on the homotopy type. So if you had anything homotopy equivalent to K3, and it's actually homeomorphic to K3, it would also have this is equal to 0, but the boundary case is only achieved if your Einstein manifold is up to covers, it's a flat T4, or it's a Calabi-Yau K3, but actually, since we're talking about a simply connected manifold, you can't have any non-trivial covers. It can only be the standard K3. All right, so the standard K3 is among this list of smooth manifolds. It's the only one that admits an Einstein metric. The Hitchin-Thorpe inequality already tells you the other ones don't admit Einstein metrics. Here's a more delicate use of the notion of monopole class. And again, we're strongly using we're using really the fact that it's a finite subset, and I'm also going to be using the fact that it is invariant under reflection through the origin. So what we do is we take this set of monopole classes sits in a certain vector space, the real cohomology, and we take its convex hull. Right? We take the smallest convex set that contains that finite set, concretely gotten by taking linear combinations of points in the set where the sum of the coefficients is 1. All right, so we take the convex hull of this finite set. Well, that is compact. You take a smooth function on it, it has a maximum. And so what we now do is we take the function on the compact set, which is for every point you have a square. So for any point in the convex hull, take the intersection pairing of that point in itself, and now we take the maximum value of that. So that is a certain number you can associate with any smooth manifold. So it's the maximum of V dot V, where V ranges over the convex hull of the monopole, of the set of monopole classes. If C is empty, then as a convention, we say beta squared is equal to 0. And then if C is not empty, we can use the reflection invariance of the set of monopole classes. So the set of monopole classes is invariant under multiplication by -1. So if you have a non-zero element, multiply it by -1, take a suitable linear, take a point on the line, is 0. 0 is automatically in the convex hull. So when you're taking the maximum here, one competitor is 0 times 0 is 0. So this maximum is greater than or equal to 0. All right? So this is a real number greater than or equal to 0 associated with your smooth structure on your four-manifold. And in particular, it's useful, you might say, why do you call it beta squared? It's useful to introduce its square root. We'll call that beta then. All right, so the notion of a monopole class is a little bit of a black box. You know, so somebody can prove that that for a particular spin C structure, you have solutions of Seiberg-Witten equations for all metrics. Then that's one of these monopole classes. All right, so if we go back to our curvature estimates, they can be restated in terms of this invariant in the following way. So for any C2 Riemannian metric on a smooth compact oriented four-manifold with V plus greater than or equal to 2, one has the following estimates. The L2 norm squared of the scalar curvature is greater than 32 pi squared beta squared of the manifold. And if you take instead the L2 norm squared of the scalar curvature minus 6 times the pointwise norm of W plus, then that is greater than 72 pi squared beta squared, larger coefficient. So the original form in which we came up with these lower bounds, we were instead saying, well, on this side we had, you took C1 for, take some monopole class, take its harmonic representatives, take the self-dual part, that depends on the metric, take the square of that, that's a lower bound. All very nice, but in fact, you know, it's still involving metric dependence. This is something, this side, the right-hand side, is now genuinely independent of the metric. And the beautiful thing, we'll see that these estimates are often sharp. So in terms of how do you prove this, if V is in the convex hull of the monopole classes, then for any metric, then you can compare. So when you project into the self-dual piece, now the convex hulls in a space with an indefinite and a product are a little bit peculiar. In a positive definite space, if you say take the convex hull and then take the point of greatest norm, well, it always happens actually at one of the corners. It would happen at one of the given points. So here, the projection of the hull of the monopole classes has as its corners has as vertices the images of the monopole classes. So there's an inequality that cuts this way. And on the other hand, V squared is V plus squared minus the absolute value of V minus squared. So it drops down this way. So for any metric and any element of the hull, there is some monopole class so that A plus squared is bigger than V squared. And now you just take V to maximize V squared, you apply that, and you find that the previous estimates imply this estimate. So it looks like you might have given up some territory in the process of getting to this simpler estimate, but in fact, in practice, this tends to still be sharp. And in fact, if you have a metric that saturates either of these two estimates, you can prove that the metric is Kähler-Einstein, and it's a Kähler-Einstein metric with s less than 0 if you're assuming that beta squared is non-zero. So that last case, the fact that this is still sharp in the Kähler-Einstein case is reflected by the following example. Suppose that you have a minimal complex surface. For simplicity, I'm going to stick to the case where b plus is bigger than 1. So any complex surface is gotten by blowing up a minimal model. And so here, I should have said this is a minimal complex surface with b1 even. Okay, we're thinking about mostly the simply connected case. All right, so in this case, one can prove that beta squared of the manifold is in fact c1 squared of the minimal model. And the fact that this turns out to be an equality in this case is intimately related to the fact that every basic class is a monopole class, and the complex structure has first term class a basic class. All right, so we'll see in a moment why this is actually. So here you can the abstract thought would say beta squared must be greater than or equal to this, because all of you can find enough monopole classes to give that lower bound for this maximum. On the other hand, because there is a curvature inequality, in order to show they're equal, one way would be to just say, well, there is a sequence of metrics on your manifold where this goes to beta squared, and that shows that you get that this is actually a sharp inequality in this case. So actually, that second curvature inequality, so this is an interesting inequality, but it's not the one you need. This doesn't come up in any Gauss-Bonnet type formulas, this expression, but you can use Cauchy-Schwarz to compare it to the integral of scalar curvature squared plus 2w plus squared. And it'll turn out, so the number that would come up as that comes up in the Gauss-Bonnet type formula for 2 chi plus 3 tau is this, minus a trace-free Ricci curvature term. And what you would find is that when you apply the second curvature inequality, that's a priori bigger than 2/3 of beta squared of m. And so what you'll find is that if you have a smooth, compact-oriented four-manifold with b plus greater than or equal to 2, if it admits an Einstein metric, then 2 chi plus 3 tau of m is bigger than 2/3 of beta squared of m. And equality happens only if both sides are 0, and you either have K3 or T4. So, by the way, among things that are covered by K3 or T4, the only ones with B plus bigger than 2 are K3 and T4. All right.
I'm sorry. Can you explain once more what is beta?
Okay, so let me go back a number of slides. This is the thing where, so we talked first about the notion of a monopole class. Right? We have a convex hull of the monopole classes. And now what you do is you maximize over the convex hull V squared. You take the intersection square of points in the convex hull. And that's certain, the maximum is certainly going to happen on the boundary of the convex hull, but it typically does not happen at one of the monopole classes, reflecting the fact that this intersection form is not positive definite. All right, so this is an example of how the way we proved the Hitch-and-Thorpe inequality was to say this expression for an Einstein metric is given by this, but then that can't be negative, right? The point is that Seiberg-Witten theory tells you more than this integral is greater than or equal to 0. You have a non-trivial lower bound for it, which in practice is often very interesting. and gives rise to various non-existence there. All right, so in the statement that, for example, you can, the statement is that if you have a minimal complex surface, and I left out a hypothesis with B1 even, B plus bigger than 1 for the monopole class idea to be correct, to really work, one needs, one would like to understand this invariant beta squared, which has been defined in a very soft way, because you might not know what all of the monopole classes are. We have some criteria that say certain things are monopole classes, and therefore the hull of the monopole classes is at least as big as a certain set, and then you can certainly get a lower bound for beta squared. That's one soft argument. But the other thing is that you can explicitly construct on all of these gadgets minimizing sequences for the integral of the scalar curvature squared. You don't know beforehand that these are minimizing, but you can approximate C1 squared to the minimal model from above by the integral of scalar curvature squared on the manifold for particular Riemannian metrics. So this is not a completely trivial construction. If X is a minimal general type complex surface with no -2 curves, what you would do is just take the Kähler-Einstein metric. You would get that this is exactly that. If it's not minimal, if it has some -2 curves, you have to you use gravitational instantons to put in some plugs to get rid of the -2 curves, and then to account for the -2 curves without really changing the integral of the scalar curvature squared significantly. And if it's non-minimal, then you need to glue in some standard models called Berns metrics. But there are concrete ways of finding minimizing sequences for this, where the infimum is exactly C1 squared of X. All right, so this is an example where you get, by one process, or algebraic process, you have a lower bound for B beta squared, just knowing that there are certain things that are definitely monopole classes. On the other hand, you get an upper bound by saying, well, this is the infimum of the integral of scalar curvature squared for sequences of metrics, and the fact that we have an inequality says that beta squared can't be any bigger than that. And now, put these things together, you get a precise value. Here's another class of interesting four-manifolds where you can compute this beta squared exactly, even though this is not done by finding all possible monopole classes. You know some monopole classes, you can also construct sequences of metrics and compare them. So the class of manifolds that I'm going to discuss is that suppose you take a bunch of minimal simply connected complex surfaces with B plus congruent to 3 mod 4. B plus is automatically odd for all of these things. So mod 4 would be either 1 or 3. Take 3 examples where it would actually be 3 mod 4. Take their connected sum, and then take the connected sum with as many copies of CP2 bar as you happen to want for a particular application. So I mentioned last time the Bauer-Ferruda invariant. The Bauer-Ferruda invariant gives you certain monopole classes on this manifold. And what you can do, it's a very similar procedure to the one I just described. That gives you that says that you have a lower bound for beta squared. You also construct sequences of metrics on this connected sum, and you find out that those two, the upper bound and the lower bound, coincide. So you actually know what this number of beta squared is for these manifolds. I don't really have enough time to go into great depth in the Bauer-Ferruda invariant takes the monopole map that we used to analyze the Seiberg-Witten equations, and what you do is you think of that map as a certain map between Hilbert spaces. And by finite dimensional approximation, you can think of that as in homotopy representing maps of appropriate dimensional spheres, and then you're taking a limit as the dimension goes to infinity. When that invariant is non-zero, you find that you have to have solutions of the Seiberg-Whitney equations for every metric, and in the basic takeaway would be if you took, in the situation I described, we have some simply connected, well here I could just allow them to be symplectic manifolds rather than complex manifolds. I'll take them to be simply connected. They all have b plus equal to 3 mod 4. You're going to take their connected sum. If you just take 2 of them, you would find that, so the second cohomology of the connected sum looks like the direct sum of the second cohomologies of these summands, or the same thing applies when you have 3 summands. And you would find then that plus or minus the first Chern class of the first symplectic manifold and C1 of the second summand, thought of as being in the Whitney sum of these, or in the direct sum of these 2 vector spaces, that is a monopole class. And moreover, you can choose plus or minus signs independently here. So this is already listing 4 different monopole classes in this case. You would get 8 different monopole classes out of this if you had 3 summands. And if the manifold, you could take one of these not to be minimal, and then there's the standard trip before you get more monopole classes just by relating the first Chern class to the first Chern class of minimal models. All right, so without going into further detail, let me just give you a very nice application of this result. Suppose you take a pair of natural numbers. You take where the first one is required to be 1 mod 4, and the bigger than or equal to 9, and required that the second one is bigger than 7/3 times the first one plus 12. Then there are infinitely many distinct smooth structures on a connected sum of MCP2 and NCP2 bar, for which there cannot be an Einstein metric compatible with that smooth structure. So the smooth structures, the smooth manifolds we're actually talking about, they are homeomorphic to this pair. So you want to take a connected sum of 3 suitable symplectic Four-Manifolds and some CP2 bars. And so one of those, we're actually putting an extra parameter because one of them, in terms of the homeomorphism type, we take this to be a K3, but here we have a sequence of different smooth structures on K3, and we could use those different K3s as the building blocks here. The X and the Y and this number K are just numbers that are determined by the pair M and N. So given an M and N, there's a recipe, which I won't bother to write out for you. There's specific symplectic manifolds discovered by Bob Gompf that you can plug in here. And given M and N, there's a recipe. The recipe sticks in particular choices there. But you're still, so the only thing that's peculiar here is that rather than putting in the standard K3, you allow K3s with this log transform. And then what you can check is that when just because you have this K3 with the log transform already tells you that there are monopole classes that whose difference is divisible by a large integer. So the bandwidth of anything of that shape will certainly be greater than or equal to 2L, where L is was the surgery degree we used in the log transform. All right, so the argument is that there have to be finite, that there have to be infinitely many diffeotypes here, is that the bandwidth is going to infinity. Now, that would be uninteresting because maybe you say, well, maybe the Hitchin-Thorpe inequality says none of those have Einstein metrics. But this shows that that's not the case. So if you take an integer, which is 2 mod 4, set m equal to p squared minus 3p plus 3, and n is 3p squared minus 3p plus 1, then this m is 1, it's mod 4, it's bigger than or equal to 9, and n is greater than or equal to 7/3 m greater than or equal to 12. That was the hypothesis. So that previous theorem says m CP2 connected sum n CP2 bar has infinitely many smooth structures for which no Einstein metric exists. But here's a concrete way of realizing that same homeotype by something very nice. You just take a curve of degree 2p in CP2 and take its double branch cover. This is a generalization of something we saw in the last lecture. I looked at a branch double cover of CP2 branched over an octet. The fact that this is twice an integer means that you can take a double branch cover. So it turns out these double branch covers also have the same, B plus is m, B minus is n, so it is, by Friedman's theorem, they're not spin, so these are actually homeomorphic to m connected sum CP2 connected sum in CP2 bar. This is a manifold in which we have shown there are infinitely many smooth structures for which there's no Einstein metric, but here is a smooth structure on the same topological manifold for which there is an Einstein metric because this double branch cover has C1 negative. The Aubin-Yau theorem says there's a Kähler-Einstein metric with lambda negative on it. So again, existence of Einstein metrics depends on which smooth structure you're discussing. So you can continue this kind of study to find lots and lots of other examples. And of course, here this is always carried out in the context. We don't really understand how to construct Einstein metrics in great generality. Kähler geometry is a crutch that we can use to create a lot of examples. In the second half of the lecture, we'll see a different way of using Kähler geometry to construct Einstein metrics on certain manifolds. But this question about existence of Einstein metrics depends on the type, on the diffeotype, and not just the homeomorphism type of your four-manifold. So let's take an intermission, and they put out some refreshments for us. Let's go enjoy them one floor down. Before I begin the lecture again, would anyone like to ask any questions related to the first part?
Bauer-Fruiter machinery, is it used exactly to get a stronger result than Hitchin-Thorpe or just to calculate the beta square?
No, it's used to get the stronger results. So, for example, in the examples that I described, so you get that there's no Einstein metric given certain inequalities, but that depends on the estimate for beta squared that comes out of the Bauer-Fruiter invariant. So you construct these particular models for that. So you construct smooth structures on certain connected sums of CP2s and CP2 bars by taking connected sums of symplectic manifolds. And then Bauer-Fruiter will give you at least a lower bound for beta squared, and therefore you get a lower bound for, well, so the theorem says that, you have to have a strict inequality between 2 chi plus 3 tau and beta squared, if beta squared is positive.
But to get to that, we did not need Bauer-Fruiter.
Yes, you did. So that statement involves beta squared. And in the application, you're using the fact that you can calculate what beta squared is in these examples. And it's positive, and it's rather positive. And so, these are generalizations of the theorem that if you took a surface of general type take a minimal model for it, right, and now blow it up at 1/3 C1 squared points, then the resulting smooth four-manifold does not admit Einstein metrics. And of course you can blow up more. It's exactly that type of theorem. It's just that this is no longer in a circumstance where you can just use the classical Witten invariant, because that classical Seiberg-Witten invariant actually automatically vanishes for connected sums like this. But some people had thought there would be no such machinery at all. The peculiarity with Bauer-Ferruta is that if you can have a relatively small number of summands with certain special properties, you still get non-trivial lower bounds for example, the integral of scalar curvature squared. What's not known is what happens if, in the same circumstances, if you have a connected sum with more than 4 summands. You have 5 summands. Bauer-Ferruta falls apart. The invariant will vanish. You don't get a lower bound, but it doesn't mean there are no monopole classes. Maybe there are, maybe there are not. Maybe there's some undiscovered method of proving that something is a monopole class. One very simple example is that if you take a K3 surface and then take another copy of K3 but give it the opposite orientation, and then take the connected sum, you can show that that dissolves. It's actually a connected sum of S2 times S2s. But if you take a connected sum of 2 K3s with the same orientation, Bauer-Ferruta will say it does not dissolve, and in fact there are, there are non-trivial results that come out of having solutions of the Seiberg-Witten equation. So connected sum of S2 times S2s has positive scalar curvature metrics. It has no monopole classes. Whereas if you take a connected sum of 2 K3s with the same orientation, then in fact there are non-trivial monopole classes on that space. So it's one of the things that is fascinating about the subject is that while we know we have a lot of very interesting results, there is so much we don't know. In particular, there are very strong results about homeomorphism classification of manifolds. There's also a beautiful stable classification that's due to CTC wall. If you take any simply connected four-manifold and you take a connected sum with enough CP2s and enough CP2 bars, eventually it does dissolve into a connected sum of standard CP2s and CP2 bars. So when you're talking about there's a kind of stable idea of how to classify smooth structures. If you're willing to take connected sums with enough standard pieces, eventually things simplify. But the range we're really interested in is actually probably very, very different. So for example, if you take a connected sum of K3 and K3 bar, oppositely oriented K3, that dissolves into a connected sum of S2 times S2s. I showed you different smooth structures on K3. For those, you get exactly the same result. But it could be that there are other smooth structures where it's more complicated, where it doesn't dissolve. You take a connected sum of the manifold with its orientation reverse. It's just not obvious. All right, so I'd now like to come to the second half of this last lecture, and I'm going to be talking about a very different subject. Most of this lecture series has focused on the question of showing that certain four manifolds do not have Einstein metrics, and that the method used to prove that actually depends on the smooth structure and not just on something like the homotopy type. But a different question that's been implicitly asked by several people participating. So why is it that you always, when you're giving an example, oh, this one admits an Einstein metric, you typically say, well, there's a Chaire-Einstein metric. And that's an example of an Einstein metric. And the reason is it's a practicality. We do not know how to construct Einstein metrics on too many manifolds without using something like Chaire geometry. I'm going to talk about a construction of Einstein metrics in this second half, which is different from the theory of Chaire-Einstein metrics, but it still uses Chaire geometry in a slightly different way. So the setting that we've been discussing in this lecture series is focused on situations where if Seiberg-Witten theory generally says if there's an Einstein metric, this invariant is non-trivial, there can't be any positive scalar curvature metrics, so if there's an Einstein metric, it's going to usually have negative Einstein constant. So then I've talked, of course, a little bit about K3, that was in the case with lambda is equal to 0. What about lambda positive? And so for this last part of the last lecture, I'm going to talk about the case with lambda positive, Einstein metrics with positive Einstein constant. And so here's a cute result which comes out of the machinery I'll be describing. Suppose you have a smooth, compact, oriented manifold, and suppose that it actually is the underlying smooth manifold of a complex surface. So it admits some integrable complex structure. And suppose that it also admits an Einstein metric with lambda positive. So here, for this theorem, you're not assuming that there's any relationship between the Einstein metric and the complex structure. It's like they live in the same large apartment building, but they've never actually met. They haven't even been in the elevator together. So if you have a complex surface and admits an Einstein metric, any Einstein metric doesn't have to do anything to do with the complex structure, then in fact, if it has a lambda positive Einstein metric, this can only happen for a certain list of manifolds, and that list of manifolds is a complete classification. So the possibilities are that you can have a connected sum of CP2 and KCP2 bars, where K is between 0 and 8. This is up to diffeomorphism. This is a diffeomorphism statement because we're asking a question, distance of Einstein metrics, it depends on the smooth structure, right? And the other possibility is S2 times S2. So this list of smooth, compact, oriented four manifolds, these all, as I've described it, these must be complex surfaces. They are the so-called del Pezzo surfaces. So there's a cute variation on this result, which is rather than assuming that you have a complex structure on your four manifold, assume that it admits a symplectic structure. So remember, a symplectic structure is by definition a closed, non-degenerate two form. Non-degenerate in general would mean that it sets up an isomorphism between the tangent bundle and cotangent bundle. There's a better way of writing this, which is just to say that if the dimension is 2m, you would require that omega wedged with itself m times is non-zero. So in this case, dimension 4, it's the same as saying that omega squared is positive with respect to a particular orientation. And here, of course, that in particular means that a symplectic four manifold has a preferred orientation. That's what we're always using if it admits an Einstein metric with lambda positive, and that is not assumed to have anything to do with the symplectic structure, then the list of diffeotypes where that can occur is the same as before. It is saying that CP2 connected to some KCP2 bar where K is between 0 and 8. This K is exactly B minus of the manifold, right? And B plus is 1. Or the other possibility is the spin manifold S2 times S2. So again, these are this set of diffeotypes. These all arise as complex surfaces. And in terms of what do we have to prove here, there are two different assertions. If you had another complex surface that wasn't on this list up to diffeomorphism, there would be an obstruction. It couldn't happen. The other possibility, the other thing to worry about is, so here we have a list of candidates, and we want to show that each of these does admit an Einstein metric with lambda positive. So the way we're going to, it turns out that not all of these diffeotypes can admit Taylor-Einstein metrics for some complex structure. There are a couple of diffeotypes here which cannot admit a Taylor-Einstein metric, but they all admit Einstein metrics. And the trick is that you can still construct Einstein metrics that have something to do with Taylor geometry, even though they're not Taylor-Einstein. All right, so so this is this statement is specifically about lambda positive, and we're talking about Einstein metrics that have nothing to do with the complex structure or the symplectic structure. So there's one version which is in terms of complex structures, and there's a companion theorem which is assuming there's a symplectic structure, but we're always talking about lambda positive Einstein metrics. And the next theorem does not involve the assumption, any assumption on the sign of lambda, but we're now going to say, suppose we have a complex surface with fixed complex structure, and we have an Einstein metric which is adapted to the complex structure in the following weak way. It is a Hermitian metric with respect to J, meaning that J acts on every tangent space by an isometry of G. So G is invariant under the action of J on the tangent space. Then this happens if and only if the first Chern class has a sign. Now this is the standard way of stating such a conclusion. That's the way, in particular, a very special case. So Taylor-Einstein metric, Taylor metrics are automatically Hermitian, but not every Hermitian metric is Taylor. The Hermitian condition is enough to say there's an associated 2 form, which would be the candidate for the Taylor form, but in the Taylor case, you'd also require that that is a closed form, it's a symplectic form. So a more precise way of saying that is that there exists such a G with Einstein constant lambda. Here, the sign of lambda will come into it. So let's, for the moment, not only choose the sign, but choose a particular lambda and ask, suppose we demand that C1 is lambda times omega. But here, there's a Kähler form in this. There's a Kähler form on the manifold. These manifolds are always of Kähler type. And we're asking that C1 is lambda times some Kähler form. But, if for a fixed lambda, it'll turn out that when this happens, so it'll turn out that the metric, it's not literally unique, but it's unique up to isometry. It's unique, in fact, up to complex polymorphisms that induce isometries for a fixed lambda. So the confusing point about this way of stating it is, so here you would imagine there's a Kähler form in this, and actually this Kähler form some of these solutions will turn out not to be Kähler metrics, and this will not in any be related to the metric. It's not its Kähler form, it's not a Kähler metric. But also, while there is some relation with Kähler geometry, it's not to this particular Kähler form. So a better way to understand this would be that you were requiring that either C1 is 0 if lambda is 0, or this is asking that the canonical line bundle is ample if lambda is negative, or the anti-canonical line bundle is ample if C1 is positive. So in particular, in this story, there is a class of complex surfaces for which C1 is positive. And so this notation, C1 is positive, means that C1 is a Kähler class. So the complication is that in general, we're not going to be looking at Kähler metrics with that Kähler class to solve our problem. But just in terms of the algebraic geometry, there's a condition on a compact complex surface when it says that it has C1 positive if C1 is a Kähler class. And you could extend this definition to higher dimensions. But in the special case of complex dimension 2, real dimension 4, surfaces with this property are said to be del Pezzo surfaces. In higher dimensions, they would be called Fano-manifolds. It's important, so Fano was a very active mathematician, and he studied some surfaces, and there are things called Fano surfaces, and they're not the del Pezzo surfaces. So it's actually a very good idea in complex dimension 2 not. There are some naive people will say that these are the Fano surfaces, but there was a different Italian classical algebraic geometer, del Pezzo, who explored these things, and the right word is these are the del Pezzo surfaces. But they do fit into the more general problem of the more general setting of Fano manifolds. All right, so del Pezzo actually did not classify all of these. He understood them in a certain topological range. The general del Pezzo surface is actually can be obtained as a blow-up of CP2 at k distinct points, where k is between 0 and 8, except in this very special case where the manifold is spin and it's instead CP1 times CP1 as a complex manifold. So what is, here you can blow up CP2 at k distinct points in general position. For example, if you have 3 points, the condition that they are in general position is that they're not collinear. So in particular, the precise statement they are in general position for this theorem is that you're going to k points where no 3 are on a line, no 6 are on a conic, and no 8 are on a nodal cubic with one of them at the node. Okay. So in each of these cases, so if you were to violate any of those properties, the issue is that if you had 3 points on a line, the proper transform of the line would be a CP1 of self-intersection minus 2, and then that would say that C1 couldn't be represented by a Kähler class, and it goes on like that. So it's basically the thing you're avoiding is by these general position conditions is that you do not want the surface to have an embedded CP1 whose homological intersection is minus 2 or anything more negative than that. Okay, so the basic theorem that I played a part in proving is that every del Pezzo surface admits a J-compatible. So here, when I say del Pezzo, I'm thinking now it has a specific complex structure with this property. Right? So every del Pezzo surface admits a J-compatible Hermitian Einstein metric, and this metric is unique up to complex automorphisms and constant rescalings. So if you like, it's geometrically unique. There is a preferred geometry. I mean, if you're happy to just change the overall scale of the manifold, that's just rescaling what is the Einstein constant lambda. But you can also, so for example, so some of these complex surfaces have a lot of automorphisms, and it'll turn out that that up to complex automorphisms, the metric is unique. In fact, one of the first things I did in the subject is every Einstein metric of this type is actually conformal to an extremal Chaire metric in the sense of Claude. Most of them turned out to actually be Chaire Einstein metrics, but there are two exceptions. Okay, so the underlying theorem about where this comes from is that any del Pezzo surface admits an Einstein metric which is conformal to a J-compatible Chaire metric H. When I say conformal, say that G is conformal to H, where these are two metrics, is to say that we could write G as some function, which I'll write as U squared times H. Of course, if you're just multiplying by a constant, that doesn't change the connection. But if U is a non-constant function, this changes the it changes the curvature of the metric in a very interesting and non-trivial way. So there are some nonlinear PDEs that arise. So if you have an Einstein metric, so in particular, notice that if H is a Chaire metric, then if H is Chaire, then it would follow that it's invariant under J. But that would then mean if you rescale it, then this would also be true. And so that would say, being a Hermitian metric is a conformally invariant condition. Chaire metrics are Hermitian, therefore anything that's conformally Chaire is also Hermitian. All right, so any del Pezzo surface admits Einstein metrics which are actually conformal to a Chaire metric compatible with a given complex structure. And in this, in particular, gives us Hermitian metrics. The interesting point is that this is something that's completely limited to dimension 4. In higher dimensions, you can find lots of examples of Einstein metrics on compact manifolds that are Hermitian with respect to a complex structure, but which are not conformally Chaire. So, for example, there's a famous complex structure discovered by Calabian and Ekman on S3 times S3. Take a round S3 times a round S3. You can now endow that with a certain almost complex structure by, on S3, choose a left invariant orthonormal frame and say J sends, let's say, the second element to the third element, do that on the other S3 in the same time, and then you can define, so send the first basis element here to the first basis element there, and send the first basis element there to minus the first basis element there. That is an almost complex structure on S3 times S3. The calculation is it's in fact iterable. S3 times S3 has iterable complex structures that make the standard product metric Hermitian. But that's certainly not a Chaire metric, because S3 times S3 can't have a Chaire metric. It has B2 equal to 0. There's no place where the Chaire class would live. So in complex dimension 3 and higher, there are lots of examples of compact Einstein manifolds with a complex structure where the metric is Hermitian. Now the product metric on S3 times S3 is Einstein, but that metric is not conformally Chaire. The theorem will turn out that in dimension 4, if you have an Einstein metric which is Hermitian, it must be conformally Kähler. And that's the source of this, the power of this strategy. So the rough strategy of the proof is to look for Kähler metrics that among all Kähler metrics, and here I'm using the notation H for my Kähler metric, and the Einstein metric will eventually be G. Okay, so among all Kähler metrics, consider this functional, which sends H to the integral of the scalar curvature squared. That's the functional part of these lectures have been obsessed with, integral of the scalar curvature squared. But here, we're going to try to minimize this not on all metrics, but just on the Kähler metrics. So this functional, so here, the key thing I want to emphasize is that we're not choosing a Kähler class. We're considering all Kähler classes, and within all Kähler classes, all Kähler metrics. Right? So among all Kähler metrics with respect to the given complex structure, try to minimize this functional. So in this problem, the Kähler class is allowed to vary. But there's a famous version of this problem where instead you fix a Kähler class. So given a particular Kähler metric, it determines a Kähler class, and only consider this problem of minimizing the integral of S squared among metrics in that fixed Kähler class. That was introduced implicitly by Eugenio Calabi in the 1950s, but he only made it explicit. That's the problem he was studying in a paper in the early 80s. So this is a problem that has a lot of history to it. But the difference in Calabi's problem, one fixes the Kähler class and tries to minimize this functional. Here, we're asking, try to minimize it while also varying the Kähler class. So if you minimize among, so the next thing is, suppose you can find a minimizer. So Calabi's, so if you have a minimizer, it in particular minimizes in its own Kähler class, so it must be one of Calabi's extremal Kähler metrics. And a different way of saying this is we want to now look at this. So every Kähler class, you could say there's a minimum, and now try to minimize as you vary the Kähler class. The space of Kähler classes is finite dimensional, right? So it's just, you're varying in the second homology, which is a finite dimensional space. And in fact, it's, the Kähler classes satisfy an extra constraint related to the fact that Kähler metrics are J invariant. Kähler forms of type 1-1. So the shock is that when you can do this, you can prove that this minimizer actually has positive scalar curvature everywhere. And then you can write down the following change, which looks completely crazy before you've actually played a little bit with the equations. I was talking about being conformal to a Kähler metric in principle. That means you can multiply by some positive function. But the positive function you actually want to multiply by is the scalar curvature inverse, that's raised to the power 2, of this Kähler metric, and the Einstein metric will then be given in this form. The fact that this is a good conformal factor was really first discovered in the early 80s by Andrei Dzerzhinsky, and he did so completely independently of Calabi. His paper came out the same year as Calabi's paper on extremal Kähler metrics, where he finally really explained the theory to the world. So one key point is that for a Kähler metric, the norm squared of the self-Duval tensor turns out to be a multiple of the scalar curvature squared. It's the scalar curvature squared over 24. Why is that, by the way? It's because of the following thing. So when you have a Taylor metric, so for a Taylor metric, the curvature tensor actually just maps the 1-1 forms to the 1-1 forms. There's another piece of the 2 forms implicitly involved here. So you in principle have an effect, but these are all zeros. So when you look at the 1-1 forms, that looks like the span of the Taylor form plus the anti-self-dual form. When you look at our block decomposition of the curvature tensor, you find, so lambda 1-1 is a bit bigger than lambda minus, but in terms of this block of the curvature, which is W plus the scalar curvature over 12 times the identity, this piece only has one non-trivial entry in it. The trace of that must be, it turns out that non-trivial entry is the scalar curvature over 4. So if you take that for granted, that for a Taylor metric, this is a strange statement, right? W plus is a conformally invariant quantity. Scalar curvature is very far from being conformally invariant, but on the other hand, the Taylor condition is not invariant under conformal rescaling. So this is not a contradiction. There's this relationship between W plus squared and the scalar curvature squared that's true for any Taylor metric in dimension 4. So if you can, so if you're trying to minimize the L2 norm of the Weil curvature, well, that turns out basically to be the same as taking the up to a topological term, which is minus 12 pi squared times the signature. This is basically the same as twice the norm of W plus squared, the integral of W plus squared. So there is a very interesting variational problem that comes up. What are the critical points of this on the space of all Riemannian metrics? The integral of W squared. It gives rise to a symmetric 2 tensor called the Bach tensor, which is given, it's usually written in terms of W, but if you write this as a variational problem for the integral of W plus squared, it turns out that you can see that this is the Lagrange equations come down to the vanishing of this Bach tensor. The Bach tensor involves a double divergence of W plus the contraction of the Ricci tensor with W plus. And here I could have written this as the trace-free Ricci tensor because W plus is trace-free. So if you look at the formula for the vanishing of the Bach tensor, though, in the special case where the metric is Taylor, then it turns out that what you're asking for boils down to something that's the scalar curvature plus the trace. This is supposed to be the trace-free Ricci tensor plus twice the trace-free part of the Hessian of S. And what Dzerzhinsky observed is that the way that the trace-free Ricci tensor changes under conformal rescaling is if you multiply the metric times u squared, then the trace-free Ricci tensor is changed by, in real dimension n, there's a part that isn't changed at all, the trace-free Ricci tensor of the old metric, plus there's an extra term, which is the trace-free Hessian of u inverse times u times the dimension minus 2. So in dimension 4, what we could go back and say, in dimension 4, if this if the Bach tensor vanishes, and the Bach tensor, vanishing the Bach tensor is a necessary condition for the metric to be conformally Einstein. If that vanishes, you can read off that this peculiar conformal rescaling to multiply the metric. So in fact, the thing you want to do is multiply the metric by the scalar curvature of the Kähler metric to the minus 2 times h. And this would only make sense globally if you knew that s was positive. Otherwise, this expression this metric would be undefined where the scalar curvature vanished. But if the Bach tensor vanishes, then you deduce that the trace free Ricci tensor of this new metric is 0. It's actually an Einstein metric. So if you have an extremal Kähler metric on a Del Pezzo surface with it turns out that it does necessarily have a positive scalar curvature everywhere, and that's a complicated calculation, but it's a general fact about extremal Kähler metrics on these Del Pezzo surfaces. All right, so one of the technical hard points here is that if you take CP2 and you blow it up into 2 points, then it actually admits an Einstein metric, which is a conformal rescaling of a Kähler metric, and that Kähler metric actually is a minimizer among all Kähler metrics of the functional, the integral of the scalar curvature square. So, in particular, so the original question about the Bach tensor came from trying to minimize the integral of, try to find a critical point of the L2 norm squared of the Weil curvature. What one can show is that actually these metrics are absolute minimizers of this among all Kähler metrics, because among Kähler metrics, these two functionals are actually proportional, but it remains unclear whether a priori this minimizer would actually minimize among Riemannian metrics. So the main statement is that on CP2 blown up at 2 points, there is an Einstein metric which is conformal to there's an Einstein metric which is conformal to a Kähler metric. And you can actually get this one way. So this is the first time, so I originally in collaboration with Xushang Chen and Brian Weber proved the existence of such Einstein metrics, but we imposed some symmetry a priori, and it was, the proof did not actually prove that these were minimizers, just that they were critical points. The second proof, you can actually come out that this metric is actually a minimizer. So one way of doing it is that you can start on, so on CP2 blown up at 3 points, there is a Kähler-Einstein metric which had been discovered by Hsu, and on that manifold that's actually the minimizer of this functional. What you can then do is take you can take a one parameter family of starting at this Kähler-Einstein metric, you can actually follow a straight line in the Kähler cone and get a sequence of these Kähler metrics which converge to the desired metric in the Gromov-Hausdorff sense. So on CP2 blown up at 3 points, there is a cone of classes in the second cohomology which are Kähler classes of Kähler metrics, and what you actually want to do, so for the Kähler-Einstein metric, if you take the Kähler form, actually the Kähler class would actually be the first Chern class, and now you want to go off to the edge of the Kähler cone. All right, so this can also be done to get a conformally Kähler-Einstein metric on CP2 connected some one CP2 bar. This is CP2 blown up at 1 point. This is less interesting though, because the metric you get was originally discovered by Stephen Hawking's student Don Page, who discovered that there was such a metric. He didn't know it was conformally Kähler and so forth, but he wrote it down more or less explicitly just by solving an ODE for this metric on connected sum for CP2 blown up at 2 points. that kind of approach does not work. The metric would be toric, but it's not homogeneity 1. All right, so the way that these things work is that for any Kähler metric, there is a lower bound for the integral of the scalar curvature squared, and in spirit, you might say this is a little bit like things we were doing with we were trying to find lower bounds for the integral of the scalar curvature squared before using Seiberg-Witten theory, but now we're looking only among Kähler metrics, and the statement is that there is a lower bound expressible in terms of the Kähler cone, where you get equality if and only if the metric is extremal, and the actual lower bound, so one of it, which I call the one term, is a more topological term, C1 dot omega squared divided by omega squared, and then there is an extra term which involves the Futaki invariant, or its norm. So I like to write this as a topological term plus a term which turns out to be a priori bounded. And so it turns out that for any Del Pezzo surface, this extra term is never bigger than a quarter. So if you take CP2 and blow it up at 2 points, then you can then work just in the realm where you have where this topological term is small. You're trying to minimize it, and then one can prove that in this range, every Kähler class is represented by an extremal Kähler metric with that with Kähler form in that Kähler class. And so if you, so one hard problem, Sue had first discovered CP2 blown up at 3 points is a very interesting example in the theory of Kähler-Einstein metrics because it has a large automorphism group. This is still a toric manifold. The worry is Sue had found that there is a Kähler-Einstein metric here in the context of these conformally Kähler-Einstein metrics. How do you know there's not another one? So, oops, sorry, I wasn't supposed to do that. That's the self-destruct button. Okay, so what? This result says that if you are in the realm where this topological term is small, it's no bigger than C1 squared plus 2.75, then there's an extremal Kähler metric in that class. And this region is actually big enough to reach out to the boundary. So, so one thing that one can show is that there's a general convergence theorem. You go sequences of extremal Kähler metrics. This was done by my collaborators Shushong Chen and Brian Weber, related to Weber's thesis. If you have an arbitrary sequence of unit volume extremal Kähler metrics on a four-manifold with uniformly bounded energies A and also bounded symbol F constant CS, then there's a subsequence which converges in the Gromov-Hausdorff sense to an extremal Kähler metric on a compact complex orbifold of the same dimension. So, so this Sobolev constant is by definition the smallest constant, which gives you a comparison between the L4 norm of a function and the L2 norm plus the L2 norm of the derivative and the L2 norm of the function. And then you can actually show that this can be estimated in terms of inverses of the Yamabe constants of metrics. So this generalizes a result of Anderson that was used for convergence of Einstein metrics and some work of Chen and Wieniawski. So, when this action functional is less than 3/2 of C1 squared of M, we call that cone in the cohomology, the control cone. And the point is that this really comes down to saying that you have a comparison between the Yamabe constant and C1 squared, 3 half C1 squared minus this action. So if this is small, this would be positive, and this would be bounding your Yamabe constants away from 0. All right, so so this virtual action, because it's bounded by something that's topological plus something that's a uniform bound on it, you're able to control this this region where you're able to understand something about the topology of the control cone. And if you have an arbitrary sequence of extremal calorimetrics, we've said before that if it has uniformly bounded scalar curvatures and uniformly bounded Sobolev constants, then either there's a sequence which, so the improvement is that either it converges modulo diffeomorphisms, or there's a non-trivial pointed Gromov-Hausdorff limit which bubbles off as an ALE scalar flat Kähler manifold. So that's the so-called deepest bubble in the analysis of bubbling. So these are not just gravitational instantons, they are asymptotically locally Euclidean Kähler manifolds of 0 scalar curvature. So the essence is you want to show that this bubbling cannot occur, and the way of doing this is that you already know that the set is open to the Kähler cone where you have an extremal calorimetric. Difficulties, you want to rule out this bubbling phenomenon, and we're on a manifold which is toric, so you can show that if this bubbling occurs, the rescale limit, the curvature concentration rescale, gives you something which is toric and ALE. And one can show that if you take the intersection form of this bubble, it's negative definite, has negative definite intersection form. In the limit, you can see that that holomorphic CP1s arise from symplectic S2s for either the sequence, and then what you can do is control this by basically a topological argument. As long as the procedure is what I drew before, you start at C1 on your, you start at the Kähler-Einstein metric on CP2 blown up at 3 points, and go out linearly in the Kähler cone, representing all those classes by extreme Kähler metrics, and you try to show that there can't be a catastrophe where you bubbled off, where you get a holomorphic CP1 whose area goes to 0. So if you get a contradiction, that can't happen. And so we actually go out from C1 along line segments. If you had if you bubbled off one of these scalar flat ALE manifolds, they all contain a non-trivial holomorphic CP1. That would end up saying that you had you would have to have a particular two-sphere representing a class in H2 where the Kähler class was going to 0 on that two-sphere. And then you can derive a contradiction from this, and the fact that your Kähler classes are combinations of C1 and some target class. So everything here would be positive. You get a contradiction from this. So you would end up concluding that you had to have a -1 curve with on which your Kähler class was 0, but the point is that for these sequences of Kähler classes, you do not have a -1. For any of these Kähler manifolds, you don't have such -1 curves. All right, so minus there you can because the class is positive on the -1 curve, it's actually positive, it's not 0. All right, so this also works when approaching the boundary of the Taylor cone, but it says the worst thing you can do is bubble off -1 curves, and that's how you can get down to CP2 connected sum 2 CP2 bar. You bubble off 1 CP1, and there's a standard bubble that rises. It's called the Burns metric. So, so what you can show is that you can, in fact, get the desired kind of extremal Kähler metrics on CP2 blown up at 2 points by taking limits of things on CP2 blown up at 3 points. And eventually one proves the following theorem. Suppose that you have a compact complex surface, and suppose that you have an Einstein metric on it which is Hermitian with respect to J. The lemma is that it actually has to be conformally Kähler, and then you can actually work back and detail what are the possibilities. One most obvious kind of classical possibility is you're actually looking at a Kähler-Einstein metric. There are only 2 exceptions. One is Page's metric on CP2 blown up at 1 point, or the metric that I discovered with Chen and Weber on CP2 and 2 points. So one of the features that comes out of this proof is that not only do you know that, this condition seems to be incredibly weak. You're just assuming the metric is Einstein and that it is compatible with J in this weak sense. But that implies it's conformally Kähler, and the conformally Kähler ones on compact complex surfaces, most of them are Kähler-Einstein. There are exactly 2 exceptions. Okay, so the exceptions occur on CP2 blown up at 1 or 2 points. All right, so going back, we said that if you had a compact complex surface with an Einstein metric on it, which is Hermitian, that would imply that C1 has a sign. By the way, this is not obvious. To prove this, the first step is to show that it is actually it's conformal to an extremal Kähler metric, and that's the thing that you use in order to get this control in the positive case. All right, so in the end, one gets a very, very close. So if you actually fix the in the Del Pezzo case, once you choose the J, there is an associated metric. In the case of these cases which are not actually themselves Kähler-Einstein, the moduli space of complex structures is a single point. So if you blow up 2 points in general position in CP2, well, you could say, well, I can blow up any 2 points, but actually by making a projective linear transformation, you can put those 2 points in any preferred position you like. There's only one complex structure in that case. So that's where the rigidity comes from. Well, if you take CP2 blown up at 5 points, say, then there's a non-trivial moduli space of Kähler-Einstein metrics. Okay, so as I mentioned before, there is this important lemma that if it is Hermitian in complex dimension 2, an Einstein metric must be conformally Kähler. And so, as I emphasized, this is a strictly 4-dimensional phenomenon. It does not work in higher dimensions. What happens in higher dimensions is completely open to investigation. There may be interesting classes of Einstein metrics in higher dimensions that have some very distant relationship to Kähler geometry, but just asking that they're Hermitian is definitely not the right criterion. And it also turns out conformally Kähler is not a good criterion in higher dimensions either. Work of Dzerzhinsky and Mashler has shown basically there are no non-trivial solutions in higher dimensions. All right, so I mentioned this notion of extreme calorimetrics before, which was first introduced by Calabi. The functional that Calabi has studied is exactly the one I've been talking about, the integral of the scalar curvature squared. What Calabi showed was that the Euler-Lagrange equations are actually equivalent to requiring that if you take the gradient of the scalar curvature and then look at the corresponding 1, 0 vector. So if you like, take the gradient of S, then plus I times the gradient of S. That's a holomorphic vector field on the you have to apply J to it. So there's a natural isomorphism between the 1, 0 tangent space and the real tangent space gotten by taking the real part. The lift of the gradient of S to be a section of 1, 0 is a holomorphic vector field, and that's equivalent to being a critical point here. That already says that if there are no holomorphic vector fields other than 0 on your manifold, an extremal calorimetric is actually a constant scalar curvature. So there's a very rich theory of extremal calorimetrics that has been built up by Donaldson and Shuzhong Chen, Mabuchi, and other people. As I was mentioning before, when you look at the self-dual Weyl curvature of a calorimetric, because lambda 1, 1 is just the anti-self-dual forms plus multiples of the Kähler form, you'll find that W plus has a very peculiar shape. It has a repeated eigenvalue. So W plus in general is trace-free. 2 of the eigenvalues here are equal, and the scalar curvature is positive. Those would be negative eigenvalues, then there's one other eigenvalue of the opposite sign. So W2 has a repeated eigenvalue, and it's a kind of amazing thing that, let's see. So, sorry, I've included slides I had not intended to include right here, so I'll just skip through this because, yeah. So the last thing I wanted to tell you about is how do you try to find, so the idea of finding a critical point of this functional, the integral of the scalar curvature squared, can be broken down into pieces. In each Kähler class, you're trying to find extremal calorimetrics, and then you want to say, well, as you vary the Kähler class, can this so-called virtual action, does it have a minimum? Does it have other critical points? So there is this virtual action functional on the Kähler cone, and you're trying to find critical points of that, and the claim is that so if you have a calorimetric on a compact complex surface with Kähler class omega, then it is Bach flat if and only if the metric is an extremal calorimetric and the Kähler class is a critical point of this virtual action. So the other thing is you can prove that in the lambda positive case, you'd have to be on a del Pezzo surface. As I've already said, on del Pezzo surfaces, you can prove that any extremal calorimetric has positive scalar curvature. So really, that leads to this statement that if you can find a critical point, then you actually get an Einstein metric out of it. The uniqueness ultimately comes down to saying that there's only one critical point. So there is this very beautiful explicit, and this is supposed to be trace-free Ricci curvature. There's an explicit formula for the the Bach tensor in this setting, and what you actually show, the place that that gives this theorem is you can show that if you have a Hermitian metric which is not Einstein, then you're on a Del Pezzo surface, and the Ricci form plus 2 IDD bar log of scalar curvature is pointwise positive. But then that ends up saying that the Kähler class of omega has a sign, of the Ricci form has a sign that ends up saying that C1 is positive, and that's why you're on a Del Pezzo surface. Okay, so the last thing that one wants to understand is, so for extremal Kähler metrics, if you have an extremal Kähler metric which is not constant scalar curvature, you have to have holomorphic vector fields. And there aren't very many Del Pezzo surfaces that have holomorphic vector fields. The only candidates are CP2 going up at 1, 2, or 3 points, because it's Del Pezzo, those are in special. Those have to be in general position. And then you can actually calculate what this, for an extremal Kähler metric, there is actually a piece of toric geometry which allows you to calculate this functional. So it can actually be described explicitly. There's a moment polygon that's associated with, so these are manifolds where you have a holomorphic action of S1 times S1. If you think of these as symplectic manifolds, the image of the moment map is some polygon in the plane. For example, if you were looking at CP2 blown up at 3 points, it would be a hexagon. But so there are a couple. So here there is an intrinsic measure coming from toric geometry on the edges of the polygon, and the total length with respect to this measure is denoted by the boundary of the length of the boundary squared. And then here, this is the area of the polygon. And finally, so those things are definitely determined by the Kähler class. And then this extra, these terms really amount to the sort of topological contribution, C1 squared over omega squared. The other contribution is that there is a preferred vector from the barycenter of, so there's a measure on the interior, just the area measure, there's a center of the polygon. There's also a barycenter of the edges. You take the vector that points from one to the other, that's called D, the difference. And then there's a center of mass matrix that's associated with those pieces. You get a very explicit formula for this virtual action. So there is this virtual action. You want to know what are its critical points. And like I said, this is something explicit, but it's not so. It's not anything terribly easy to understand. You can't just look at this and say, oh, that has only one critical point. So here the variables are. This is done in the case of CP2 blown up at 3 points. You normalize the Kähler class to be C1 plus some multiples, so these gammas and betas, alphas, these actually represent the areas of certain curves, and you get a quotient of 2 complicated looking polynomials, and you'd like to claim this has exactly one critical point, and you can't, I mean, if you feed this to a computer, it'll sort of say, it'll chew on it for a long time and then say, yeah, here's a critical point, I can't find any more. But to get a proof, what you need to do is instead say, you first use that formula to show that there's a certain partial convexity of this action. You have this, you show that, so there are some automorphisms of M, topologically, which is you interchange 2 of the exceptional divisors corresponding to blow-ups. And then what you want to do is ask if you take a Kähler class and look at its image under this automorphism, join them by a straight line, I claim that this A has a certain convexity property. So it's actually convex on appropriate lines, and what you end up doing once you know that, so for example on 3CP2, once you know that it's invariant on under these automorphisms, it reduces the problem to one. It looks very intractable in all of these variables that you're ultimately you end up finding if there's a critical point. If there were, since this is convex on that straight line, on a convex function on a straight line cannot have more than one critical point. It has to only, if it has a critical point, it has to be at the center that you've reflected across. So using some ideas along these lines, you can eventually show that first, on CP2 loan at one point, the page metric is the only candidate. There's exactly one candidate, which is the one that I found with Chen and Weber on CP2 loan at 2 points. And if you do this on CP2 loan at 3 points, the only critical point is actually at C1. It's the metric is actually Kähler-Einstein. That's the SU metric. And so that eventually gives rise to the theorem. All right, so finally, I mentioned a classification result at the beginning. If we knew, if we're just asking, suppose I have a complex surface, suppose it has an Einstein metric, and suppose that that Einstein metric had positive Einstein constant, then it turned out that we were able to get a complete list. We got a complete list of the things that could have such metrics, where the Einstein metric is not necessarily related in any way to the complex structure. And there's a generalization of this. If we require the Einstein constant to be greater than or equal to 0, the only assumption is our four-manifold is the underlying four-manifold of, our smooth four-manifold is the underlying manifold of a complex surface. You have an Einstein metric on it, assume that lambda is positive, then you have a complete list of diffeotypes, CP2 blown up at K points 0 to 8, S2 times S2, but we know about the K3 surface. The K3 has a Z2 quotient called the Del Pezzo surface. Then we have the flat four torus, and then there's a finite list of finite groups that act on the four torus by isometries. What one can prove is that this list is up to diffeomorphism type. These are the only possibilities. And in fact, if you're below here, it's basically by using the Hitchin-Thorpe inequality for the added things, the only Einstein metrics would be when, so these would all be lambda equals 0 Einstein metrics. They're actually either locally, these are all locally hyperkähler metrics. So the things one gets are the Del Pezzo surfaces, K3 surface, the Enriquez surface, so-called abelian surface, which is a four torus, and hyperelliptic surfaces, which are these quotients of the four torus. And there's also a version of this which works just assuming that we have a symplectic form on the manifold. So there's another aspect, another application of Seiberg-Witten theory, which I have not talked about in this course. There's a beautiful work of Taub's, which allows you to use the Seiberg-Witten equations, or more strictly. So that there it's important to take a specific large perturbation with where the thing you're perturbing by is a multiple of the symplectic form. And what Taub's was eventually able to prove is that under suitable circumstances, you can predict the existence of a pseudo-homomorphic curve, and then using results of McDuff, you can tend to classify, under certain circumstances, you can actually classify the manifolds up to symplectomorphism. That's being used very strongly in the case of Del Pezzo surfaces. So this is really using results of McDuff, Otto, and Ono for the first cases. But so it's more classical if you assume that you have a complex structure here, and it comes down to saying which complex surfaces could admit positive scalar curvature metrics, which ones, and if it doesn't admit positive scalar curvature, but it admits zero, well, you get into these realms. The interesting point, and I will be giving you a bibliography to go read more about these things. You can also understand the problem if you impose the existence of a symplectic form on your manifold. So this is not a classification. If you just say which smooth manifolds admit Einstein metrics with lambda greater than or equal to 0, we have no way of answering that yet. But here are two interesting extra hypotheses you could put in. One, suppose that it has a complex structure, or suppose it has a symplectic structure. In those cases, then in one direction, you can eliminate everything that's not on this list, and in the other direction, you can show that everything on this list admits an Einstein metric, and in fact, in most cases, they're Kähler-Einstein metrics, but in two cases here, to fill in the missing gap, we have to step outside of just looking at Kähler-Einstein metrics and look at conformally Kähler-Einstein metrics. So not every delta surface admits Kähler-Einstein metric. There are two that don't, but those turn out to still admit preferred Einstein metrics, namely metrics that are conformally Kähler. Okay, so that leaves open the following. So there are various natural questions. Suppose you have, throughout, often our examples of four-manifolds have been look at the underlying smooth four-manifold of a complex surface. Suppose that a complex surface has an Einstein metric on it, where the Einstein metric doesn't have anything to do with the complex structure. All right, so if lambda is greater than 0, we've already seen you can completely classify this. But maybe lambda is negative. What can you say then? So if it's not on the list of things we've just seen, the first thing is you can show that the complex surface is necessarily a surface of general type, and it's not too non-minimal. So it might. So if you're looking for a Kähler-Einstein metric if you have a complex surface and you're asking, could it have a lambda negative Einstein metric? The complex surface has to be minimal. It cannot be the blow-up of something. And the gap in our knowledge is that, well, maybe it is non-minimal, but it can't be too non-minimal. You couldn't have blown up too many points. So you have to have blown up fewer than C1 squared of the minimal model divided by 3. And actually this result, again, if you just assume that your manifold is a symplectic manifold, you get the same kind of conclusion. But what would you mean by saying that you have a symplectic four-manifold of general type? The correct notion is again stated in terms of you have a minimal model where C1 squared of the minimal model is positive, and in addition, that minimal model in the symplectic category is a symplectic manifold, and you ask C1 dot its symplectic form is negative, where this product is the intersection pairing. All right, so in the lambda 0 case, the questions that this really naturally leaves us with are there any non-minimal complex surfaces of general type that actually admit Einstein metrics? Right? So minimal surface of general type, well, with a very mild extra condition, which is you can usually get rid of by deforming. You don't want any -2 curves. Usually, minimal surface of general type admit Kähler-Einstein metrics. But if you look at just Chaire-Einstein metrics, you're limited to minimal complex surfaces, and the gap in our knowledge now is that it's conceivable that there are some non-minimal complex surfaces that haven't been blown up too much that might admit an Einstein metric. Any result in this direction, I think, would be fantastic. We can improve and give a partial answer to this question. An improvement on the number of blowups, for example. Another question is, are there any non-complex symplectic manifolds of general type which admit Einstein metrics? So there are a lot of symplectic form manifolds that you can prove do not admit complex structures. They cannot, the almost complex structure associated with the symplectic structure cannot be deformed to an integrable one. Can any of those admit Einstein metrics? Again, we just don't have any machinery. Oops. And so, I mean, if there were such things, the main thing we could say about it, this is stupid. These would have to be Einstein metrics of a very different ilk than anything we know how to construct so far. And so, again, an interesting challenge. Can you think of some way of constructing Einstein metrics on some symplectic form manifolds that does not come from Chaire geometry in some way, shape, or form? So I've already told you what the answer is. If you weaken the condition to simply require the metric to be Hermitian rather than Taylor, you almost get the same answer. There are two exceptions. You get two Einstein metrics of general holonomy, which they're not Taylor, but they're still conformal to Taylor. All right. So when you are able to download the slides, you'll find two different reading lists. The first is a list of some papers where they're either by me or by me and collaborators. And then there's an additional reading list for various background on Seiberg-Witten theory, Bauer-Ferrutta theory, and so forth, and other related topics, extremal metrics, and so forth. So, with that, we've come to the end of the series. I hope you found it useful, and thanks for attending. So, do you have any questions? I'm sorry, the part on extremal metrics and so forth, I wasn't careful enough in putting the slides together, so put in some things that I shouldn't have, and I put in some slides that I shouldn't have, and I left some things out. So maybe you need some clarifications on those in particular.
Can you give some suggestions on how to bridge the gap between Witten and your work? Because so you said you don't understand everything Witten says. Probably you cannot prove everything he says. But
yes. So one of the fascinating things so Witten's original paper where he introduced the Seiberg, what we call the Seiberg-Witten equations. Seiberg didn't have anything to do with it, so far as I can tell. It's a misnomer, but at least we know what equations we're talking about. So Seiberg was very, very peripherally involved in other things in physics. So Witten had a physical argument claiming that when you quantize Yang-Mills theory, that it becomes equivalent to Seiberg-Witten theory. And so that Seiberg-Witten theory and classical Yang-Mills are two different limits of a quantum field theory. And the physicists I've talked to about this, some of whom are very good physicists, don't understand the argument. No mathematician understands the argument. And there is a mathematical attempt to find a direct translation between Seiberg-Witten and Donaldson invariants due to Feehan and Linnes, which has been partially successful in certain circumstances. The connection seems to be mathematically pretty plausible, but it's still the case that in general there is a lack of understanding. And Witten's comment on when Feehan explained to him what they were trying to do, he said, if that's right, my own understanding must have been completely wrong. So it's a quandary. I mean, that way of trying to find the Feehan-Linnes program tries to find a connection between Donaldson invariance built out of Yang-Mills instantons, moduli space of Yang-Mills instantons, and Seiberg-Witten theory. That is it seems, if it works, the connection is quite different from the physics argument. So I can't judge whether the physics argument is basically correct or not. I don't know any physicist who has claimed to really go through and substantiate the details in that argument. There is a leap. Apparently, the physicists say they understand part of the argument, and then there's some kind of leap of faith. And from a mathematical perspective, the thing that can be verified is that in certain circumstances, like for compact complex surfaces, the Donaldson invariants are completely determined by Seiberg-Witten basic classes. On the other hand, for example, there is a rich side of Seiberg-Witten theory, like the Bauer-Furuda invariance, where I don't think there's any known analog in the study of Yang-Mills instantons. So I certainly take Witten's claim seriously, but I'm afraid I cannot technically evaluate, and the people that I do know that would be in a better position claim that they, this is one of those heuristic arguments in physics where there's a huge gap, and it may be completely correct, but if so, I mean, it's very surprising though to a mathematician, because Yang-Mills equations are conformally invariant. If you change the metric by multiplying it by a function, the Yang-Mills equations are completely unaffected. But so the essence of Witten's argument is that in order to quantize the theory, you have to choose a particular metric, and somehow you break conformal invariance, and at the other side of the story, you can pop out a theory which is definitely not conformally invariant. So the sorts of things that we have been using, the mathematical uses I've put Seiberg-Witten theory to have been for understanding things like the integral of the scalar curvature squared for a Riemannian metric. I'm trying to find lower bounds for that. That functional is not conformally invariant. In any conformal class, you can make it go to infinity. The curious thing is that there is a lower bound. It's not a contradiction, but it's an unexpected lower bound. I don't know of anything in Yang-Mills theory. One of the reasons I got very, very interested in Seiberg-Witten theory immediately when it broke was that I was interested in certain questions involving, for example, the scalar curvature of complex surfaces, and then to realize that there's actually some world of an area of Riemannian geometry where one could get a lot of traction suddenly. It was a surprise and exciting. So, I wish I could say something intelligent about the connection between Donaldson theory and Seiberg-Witten theory, but so far as I know, the level of mathematical understanding of that connection is still very limited.
So there is another word of Seiberg-Witten theory which is considered a family version.
Yes.
And do you think there can be some application of family Seiberg-Witten? For example, on K3 surfaces, the Seiberg-Witten invariants vanish, but there is a family version of the.
Yes. So the person who really pioneered that was Danny Ruberman, and at Brandeis, and he used this to prove some amazing theorems. So, for example, when you look at there's an obstruction to, if you have a non-trivial Seiberg-Witten invariant, your manifold does not emit positive scalar curvature metrics. But he was able to show on certain manifolds that do emit positive scalar curvature metrics that the space of positive scalar curvature metrics is not connected. That you could find paths so in particular, what he was really interested in was so if you have two positive scalar curvature metrics, can you join them by a path of positive scalar curvature metrics? And that's a family's problem. Right? So you have a family of metrics. What he was able to show that in certain circumstances, there was some catastrophe that had to occur because suddenly at the expected dimension of the moduli space might be -1, and that means that on a curve you could suddenly have just discrete points at which the invariant became non-zero. So so he was able to generate examples of four manifolds where there was more than one connected component of the positive scalar curvature metrics. In his particular examples, the examples that you actually look at are geometrically the same. Namely, you take a particular positive scalar curvature metric and you move it by a certain diffeomorphism. And then you get another copy of it, but it turns out that you can't find a family of positive scalar curvature metrics that joins them. So there are some amazing phenomena there. I think that family's invariant, the family's version of Seiberg-Witten is a very interesting topic. And so in particular, it would be, from my point of view, very interesting. So this is about asking about the number of connected components. But in principle, one might be able to show something about higher homotopy groups in the space of positive scalar curvature metrics by showing that that you can't find higher dimensional families with certain properties. That let's say a certain map of a sphere of a fixed dimension into the space of positive scalar curvature metrics can't be filled in by a map of the disk. So I think that's a potentially rich area. So if you're learning about such things, you might. So I have seen some nice applications of this to differential topology, but in terms of applications of these observations to studying things like the space of positive scalar curvature metrics, I haven't seen anything except LeBrun's original article. Good question. Questions, comments? Well, I thank you for your patience, and thank you for coming, and I hope that it's been useful.